you have to prove this
Okay, let's start with the next speaker.
Really rely on.
Okay, yes, hello and welcome. So my name is Kathrin. I work at Harvard University. And today I'm going to give an overview talk on the Autosubst Library, which is a library and tool to simplify reasoning with binders. Fitting to the topic of the workshop, I will put my focus of this talk like less on the technical details, a little bit more like on the library aspects. But if you're interested in any of the technical details, of course, like come to me talk afterwards. I just try to keep this like a little bit more general for today. Okay. So today's talk, I will split into two parts. So first, I will talk about like the core Autosubst library, which is a library of binders, and then I want to use the second part to talk about an extension, which is a little bit orthogonal, but also like basically targets how to have a library for programming languages proofs in Coq a la carte, or like how we could have a library for modular proofs. The second part is a little bit more work in progress. Okay, so let me start with the foundations of Autosubst and like what Autosubst is about. And there is one central question, and the central question we have for Autosubst is what do we need to know about the formalization of binders if we want to write proofs about programming languages in a system? This has, of course, been this is, of course, like the central question. If you like want to design a library, like what do people actually like know to know about background? Like how much do they actually like need to be involved? This has been the topic of a now 20-year-old paper called Mechanized Meta Theory for the Masses, the Popelmark Challenge, which mentions explicitly like that binding is one of the more one of the core concepts about like how to do programming language research and like how we can treat alpha equivalence. One would think that 20 years are enough so that people get a consensus on what to do in this case. This is still not the paper, like it's still not the case. There's still like papers published on like maybe it did like just slightly different representation, maybe another way to basically reduce some of the boilerplate code. I think alone at like last Popel there were like 2 papers around this. There's a paper of like one person here in the room at LFMTP. So this is still like a topic, even if it's like 20 years ago, people look at it. So if you look at a textbook proof, how would we treat variables in a textbook? It mostly, many times, stay implicit. This would be not the case where it's a little bit explicit. This is from lectures of the Curry-Howard aristomorphism. So we would first like define something like pre-terms, where we basically assume that don't assume alpha equivalence. We would then define on these pre-terms something like alpha equivalence, define the actual terms by having a quotient over terms with alpha equivalence. And then if you would write definitions on the actual terms, not the pre-terms, what we would actually do is we would want to write functions on this quotient of the terms which we have. And like on paper, most people would gloss over these parts. So Yannick mentioned yesterday the term of invisible mathematics, and this would be exactly like one of the examples of this. So if you would look into typical proofs, most of these details would be glossed over, even if it's done fairly explicit, like in this book here. It would say something like, well, strictly speaking, we would have to demonstrate certain properties of this. We would have to show that we have the functions which we define are valid. But in the rest of these notes, we don't care about this. We'll leave all of this implicit. And of course, we can't do this in a proof assistant, and the proof assistant won't be convinced if we say we leave these parts implicit, but we actually have to define those and care about those. So we would have to think about what would be a representation of binders we are talking about. We would think about how we explicitly state substitution, whatever we are talking about. And then also we would not be able to gloss over this kind of proofs, but we would also do these proofs about substitution. And these proofs about substitution, they can get ugly and they can get big. So this would be one example of a proof where we would simply want to prove substitutivity of reduction, so that like if S evaluates to T, then like S is substituted as sigma evaluates to T and to substitutes of sigma. And the statement here, like stating like certain properties would be like a one-liner, basically, or even like be glossed over in a text proof. But if we would, for example, want to do something like that in the Brown notation, like this would be the kind of proof if we would actually like want to split out the lemmas. So we have to care about like that, like substitution is compositional. We would have to have like something like distributivity, associativity, etc., which like brings up the question of like which lemmas do we need? How do we apply them? Like what exactly do we need to know about substitution? Do I basically have to know like which lemmas exactly I want to use? Do I always have like to write these proofs? So we come back to the question, like how much do we need to know about the formalization of binders to write proofs? Do I basically like need to like read all the binding papers, like know what the substitutions are, etc., to actually be able to use such a thing in a proof assistant? Okay, to make this a little bit explicit, there are different like levels of like what we would need to know. So given that we have like decided for a presentation on like how to have binders, we would have to know like how to state lemmas in this presentation. But this is enough. We would like also need to know like which lemmas on substitutions we would have to prove. We would know like how to prove them and like how to use and apply them later on. So the hope of a binder library such as Autosubst is that we basically just like have to know like how to state lemmas in this presentation, and then there is like some automation or like some tooling which relieves us on the later parts of this, like me not necessarily like needing to know like which exact lemmas on substitution itself I would still need to know, for example, like how evaluation, for example, behaves with substitution, but like substitution alone, that I wouldn't have to know this kind of lemmas, and that some of this is like proved and like automatically from me. Okay, so the Poppermark challenge, which I mentioned before, has some criteria for success for such a representation, which I think is also kind of interesting, like for library design in general. So it mentions that like if we have such a technology, it should be impose some like reasonable overheads. So we wouldn't like need to write like pages and pages for this. It should be transparent. So we should in some way be able to like translate from this on what I have on a paper representation, and it should have a reasonable cost of entry. So here it says it should be usable after say 1 semester training with someone who's knowledgeable about programming language theory, but not an expert in this topic. And same, of course, like would also go for binders. So the question is like how can in particular like go for a representation which has a reasonable cost. Okay. So the Autosubst library is one approach to this question. And I would summarize as it being like one choice of binder representation, definition of substitutions, and set of substitution lemmas that, as chosen, requires minimum input from the user. And second, some kind of automation or tooling to make this applicable to like a wide range of syntaxes. That again, like so that like there's no boilerplate and that requires minimum input from the user. I say explicitly like a choice of a binder representation because really there's a lot of research like way before Autosubst, like basically like having this. I think the more important part is basically like bringing this together in a tool, and like how to choose like how to choose it. What is a nice representation? Okay, and I will focus on the tooling part today. Okay. So as I already hinted on, there's a variety of binding techniques in proof assistance. So these are just like a table from the Poppermark challenge web page, like of some of the formalizations which there have been in the first years after this. And it goes basically from choices of like we have a special purpose proof assistant which supports us in using binders until like we have like some like definitions we can use in the general purpose proof assistant, just like as for example ROC. There are also like multiple definitions, for example, in several proof assistants. So really it's like this range of like different approaches and like libraries to this one chapter, which I think makes it interesting to like look at from a library perspective. Okay. The one which Autosubst uses is it uses the Brown syntax. The Brown syntax is, of course, is the oldest of them all, right? So we have basically make the trick that instead of like having to define alpha equivalence and then the quotient, we don't use names, but we use reference to the binders, and hence basically save us the trouble of equivalence and defining the quotient over them. So, for example, this would be an inductive representation in Coq of a syntax of terms with the Brown binders. So a variable is a nut. And like implicitly, if we go under a binder, we induce a scope change. So we see in this case here, we have this like variable z, which then in the Brown would be 1 like on the upper level under the x. But then if we go like 1 level deeper under the y, we would basically like have to lift it explicitly. So we have this like scope change if we go under a binder. Okay, so why did Autosubst use the Brown? I will show some reasons further along. Main reasons are it's usable in a general purpose proof assistant. So I don't need like something like higher order abstract syntax. I don't need, for example, like something like Beluga, which requires modal type theory. It is some representation which is very well understood. Because it has been used for a long time. There is lots of papers around about like how to extend it to different kinds of syntax. And the last point is that, as we will see, it actually allows us to do some automation, which can be purely by rewriting, and which allows us a rewrite system so that we actually don't have to care about the numbers, but we actually just have to care about the representation. Okay. So we use the Brown syntax as our syntax. So as I said before, it's a thing of like we have to define the syntax, we have to define substitutions, and then we have to think about like the kind of levers we need about this. So let us go to the second part, which is about the substitutions. Substitutions, again, we will use what the Brown already defined. We will use parallel substitutions. So what we want to have is we want to have an instantiation with substitutions. And we want to have an instantiation with parallel substitutions, means that like we have a substitution which is a function from nut to terms. So all variables are replaced at the same time, and then we get again it. And we will use some primitives on how to define the substitutions. These are some primitives which have like before known also like in type theory, or they have been also like, for example, used in sigma calculus. And these primitives which we are there, they're first sufficient to basically like go under a binder and like talk about the scope change. And second, they are sufficient, for example, to define something like beta reduction. So we can basically like use them to use the usual programming primitives we want to use. Okay, so what are these? We once have like identity. So this is like basically something which basically like just like stays the same. So we don't do any scope changes. It's a shifting. So basically like imagine like every variable basically being replaced by like the variable plus 1. And then we have the cons operation, which replaces 0 by s and then like continues as a previous substitution. Okay. With this we can define substitution. So we basically go over the whole term functorially. So in the case of like a variable, we just like look what our substitution says about the variable. In the case of application, we basically go into by both parts of the application. And in the case of Lambda, this is where the interesting thing happens. We basically like have to care for the scope change, which is implicitly there. So what we do is we use like s, and then we have to shift the sigma, meaning that like the first variable, which still by like the 0, we can't replace it because like it's just like a newly bound variable, and all substitutions in sigma basically have to be like which European substitution have to be looked at. Okay, looking at this definition, we see that implicitly we basically like do recursion in ourselves, in that like this definition of substitution requires like this composition basically requires substitution itself. So it's not structurally recursive as it is. So if you do this in a proof assistant, we would actually need to a two-level approach where we first define instantiation renamings for which this composition is just like usual function composition, right? So we just like have basically like two numbers which we compose. And then we can like define instantiation with substitutions after. There is a current paper at this year's LFTP. One of the authors is in the room. How to do this like without this two-level approach. This doesn't work in ROC. Like it would work in ROC, but it would be more complicated. Basically, like we would need to use a lexical termination procedure, and like in this case, we would basically be able to save us the thing of like first defining substitution with renamings and then like substitution with actual substitutions. Okay. So now we've defined substitution, and now let's go to some of the proofs. So I already mentioned that a proof of substitutivity with de Bruijn might look something like that, and that's an actual proof with like definitions we have done before and with what's in lecture. So this is a kind of like lemmers we would need, and here of course like the question is like, how do we know which lemmers we would need? Do we need to do this manual? The good answer to it for us is that this has already been like considered in the so-called Sigma calculus by Abadi and others, which had a slightly different focus. But they talk about a rewriting system and define a rewriting system for substitutions, which looks something like that and uses the primitives, which you just like have seen before. Say something, for example, that substitution like distributes. It has some properties about identity and compositionality. And the even better thing is that this system is both convergent and complete for the de Bruijn algebra. Convergent meaning if I just like apply these kind of rewriting rules, I will result in some kind of normal form. Complete meaning if I don't have any assumptions in my context, I can basically decide equality up to like this like substitution definition without having to know anything about like the exact like rules which I have, right? So this can be decided via this above rewriting system. And once we have proven this kind of lemmers, we are basically like done if you're good at like having substitution for lemmers. So let me show, and we can implement all of this, of course, like relatively easy in a proof assistant by using a rewriting tactic. In Autosubst, this is called a simple, which basically normalizes this according to this rewriting system. Let me show you an example. So we might, for example, want to do a proof of type safety. So we have here a definition of like evaluation, stepping one step. We have the definition of beta reduction, like step of like application, like a lambda and a t, where we use this definition of cons and like use a primitives defined before, where basically like the zero variable is replaced by t and everything else basically like that. And if you want to prove that step is substitutive, so that like if step as t, then also step substituted with sigma on both sides and holds, we would do the usual proof by induction. We would basically stop at this like proof which I've shown before, which would like look something like require us to solve an equation as that, and looking like this. But using the simple technique, this basically like simplifies to some normal form, which is exactly the same thing on both sides. So all I basically like have to do is like use a reflexivity example. Okay. So I said that Autosubst is both this like choice of binary representation. We have seen now how this binary representation would look like for the lambda calculus. The second thing it is basically like a way to scale this up to like more kind of syntax. Because even if you know how to do this for the lambda calculus, we would have to basically like prove the same lemmers again and again if you're talking about like more vast syntax definitions. So you might ask, is it so bad to like prove this kind of lemmers which I've seen on the last slide? And the answer is yes, it is so bad. Let me give you one kind of quote, and then let me give you an example. So this is from one of the authors of the Poppermark Challenge, and one reason why they basically said that the brown would be unusable is that they said that all this clutter is manageable if I have a small language. But if I speak about a bigger language, a fairly small even something like F-sub, like it is defined in the Poppermark Challenge, it basically gets quite a heavy burden. So some libraries and tools for the rescue. Let us see how this would be on an example of for example, system F call by value. So this would be the example how for example, I could define some kind of the types and terms for such a system. Then I would define substitution on this. This is still fine, right? But I would basically have to care that if I do substitution, I have to do substitution on the terms and values. And if I go under the binders, I basically have to account for me going under a value binder with a type substitution, me going under type substitution with a type, basically this goes up. This is quadratic in the number of binders which I have. And well, this would be an extract from the proof. So here you would see basically the proof for even a small signature as we had before. So basically this is a lot of boilerplate. And yes, we can prove this by hand. It's not impossible, but it's also boring. And actually, if you want to change your definition of the syntax, you wouldn't want to do this manually every time. Okay. So like I said, one main culprit is the instantiation, and then we have this kind of different substitution operators. And also if you have this approach where we have both instantiation with renamings and substitutions, even to show something like compositionality, which is one of the lemmas which we have basically seen, would basically require 8 intermediate lemmas to prove this. Again, this wouldn't be you can do it, but it's also boring to prove this kind of numbers. Okay, so what Autosubst does is it is this choice of binder representation, but it is also this kind of library format to automatically generate the corresponding boilerplate, including an automation tactic. Okay, and so I should say that how Autosubst generates things, we will see in a moment. It basically gives us basically a file with all the output is not the only solution to this. And some people might say that it's not the right solution for a library, and I won't argue about this, right? So they're different. I think there are different approaches which have different pros and cons. So it goes basically everywhere from basically you have your special purpose proof assistant, which removes all this boilerplate. Basically has it built into the type theory of the proof assistant. You could have something as code generation, which basically gives you the output file, it gives you the definitions. You could have something with meta techniques, or you could also define something with universes of syntax defining, which basically means you have one representation of what a syntax is, and then you basically define on this representation what substitution is. So the way Autosubst does it is it basically takes some kind of specification file, defining basically how we want our syntax to look like. So this would be the example of of lambda calculus. We have just application, and we have lambda calculus, which binds one term binder in its one argument. And the Autosubst compiler would then give us an output file containing the expression, the instantiations, and the whole reasoning principles which we need for this. Okay, you might notice that in this case here, it doesn't have the case of the variable case. This is because it's automatically determined which substitutions are required based on these bindings we have in these different constructors. Right? So automatically some kind of dependency graph is built in the background and tells basically oh, for example, if I have system F call by value, types just require type substitutions, but no values appear in these types, so I don't need any substitution of values in it. If I have terms and values which are mutually inductive, both of them would both be able to place type variables and labels. What is the kind of supported syntax? So this kind of supported syntax would be polyadic binders, so it can bind both a type and a term variable. I can have a first class remaining, so we're renaming so explicitly like this function is like match to net. I can have some external sorts or sort constructors in my signature. I can have like many sorted syntax, mutual inductive syntax, periodic syntax. And there are also simplified definitions for first order sorts and modular syntax, which I will like come to in a second. Okay, so let me quickly check the time. I think I will save myself this. So like this is just like basically like we can basically like extend the usual primitives which we would have for vector substitutions and for periodic syntax. So basically we can like use the same principles for this extended syntax, and it basically like behaves very nicely with exactly the same approach. Okay. I should say on the library side that there are different versions of the Autosubst library. So the first one was implemented using LTAC, but quickly came basically to its boundaries because like we couldn't like for example something like mutual inductive types weren't possible at the time, and we could also like not, it was difficult basically to find even something like several substitutions on one sort on how this was defined. From this it went to an approach where it was more code generation like, so there was a implementation Haskell and then a camel version, which is the most up-to-date version. And I also recently learned that there is some lean emulation, which uses a simplified like simplification tactic by lean instead of like having to define a simple ourselves. Okay, there are some trade-offs to this. So like I already mentioned like that, for example, on like how expressive things are, on what can be generated, how maintainable is this for different versions of Rock. In general, like the code generation has one like advantage is like because it generates proof terms, the proof terms are relatively stable. But what it really gets like messed up, like so we heard I think yesterday that like lean basically doesn't have a like problem with like tactics, etc., etc. But in Rock, like changes in the notation system, etc., basically like probe previous code which has been done before. And also there is a question whether we are interested in whether the code can be inspected and changed manually, which can be a benefit for some of the users who might be happy like with a basic file, but then might want to, for example, to have some extra definitions, might have some extra features they want to add later on, which I will mention in a moment. So these are some of the projects using Autosubst or Autosubst 2. So it's mostly things doing programming language research. There are some things on the first order library, for example, about a completeness theorem for first order logic, I think, which is part of the library, which Yannick talked about yesterday. So this paper here, this version here, basically like used the Autosubst version for this. Some bits on this. So having these developments was very useful in extending some of the features, for example, like having a simplified version for first order logic. It also informed, for example, an early version used functional extensionality to define this rewriting tactics. Later versions did it and actually doesn't require it. And this was also like informed because like some of the developments were really, really keen on not having any extra assumptions. I mentioned that some of the developments basically like use Autosubst as a basis and then like do some changes or like some additional definitions. For example, this paper here, which with also Mevin, hi Mevin, uses Autosubst to have like some syntax optimization for the meta theory of Martin-Löf type theory, but then also it needs an additional definition of like well-typed weakenings, which can just be added because you can basically like inspect the file and it's not generated by the syntax. So I guess like I would see this as an advantage of basically like having this explicit coq file, which you can basically like change, add on if there are not features, like even without you having to understand basically like how Autosubst does it in behind, but you basically like have this file which you can inspect and like can make like work on.
also had to extend the tactics, and for this it was also quite useful to be able to look at the original ones and then extend with our own primitives, I guess.
For example, also like the work, like some of the work around first order logic, like started with an Autosubst definition and then basically like adopted some of the approaches until like going to something different. So like being able to manually adapt this, I would say is actually an advantage. Some other things which were picked up, interesting enough, even though this is a proof library, something which came up like from the start is sometimes there were performance issues with like rewriting. This is a problem, for example, in this approach. It's also like a problem in like work of Kimani and Birkedal. And one solution to this is to not use just like simple rewriting, but actually like define this a simple tactic as a like reflective version to like get rid of the bottleneck of rewriting. Okay. Another thing is we'll just like gloss over this, like in like how to like basically like ensure that the lemmers that the user writes are basically like don't introduce any like wrong shifts or lifts, which is a common problem in Autosubst. So one of the target syntaxes is that users can also like target scope syntax and not just unscope syntax. This has other disadvantages. So I would say like having the choice for the user is a good thing in this case. Okay. Let me finish this part by talking about some other binder supports in some libraries. So one thing is that it would be useful to have support not only for decidable and assumption-free things, but also be able to basically do matching with assumptions, which again, like appeared in some of the developments which I was talking about. There is recent work on like how to support like traversals over syntax with binders. For example, there is work by Alain and others in Actor. There's also like some Isabel development around this. There is work on intrinsically encoded inductive types, and also like a recent topic has been like how to extend this kind of like libraries and supports for substructure language. So for example, this is one approach which extends on like the work of Alain and others, one for substructure language, and there was also a paper at this year's CPP which actually won a distinguished paper. Okay. And I think with this, let me go to the other part. So we talked about like having a very specific problem, about a very specific solution with the Autosubst library. Another problem is if you like build this kind of libraries, you have proof libraries which are useful, but by how can they basically like cope with inductive proofs? So most of the definitions I would write in a programming language proof would be like all based around inductive proofs, and like this is by design like this. But sometimes I would like to extend this kind of inductive inductive proofs I have. So for example, we might start with something like the lambda calculus, and we might want to give like recursive definitions on terms, proofs by inductions on the terms, and like predicates and rules, predicates and proofs over these terms. And then we might like later want to extend this calculus, for example, by Boolean expressions. And by extending, I mean that it's not necessarily as regular as in the case of substitution that I know exactly like in which case, like which to do exactly, like it's basically just like functor over the syntax. But it still has like some regular in that these proofs don't interfere. For example, if I have type safety proof, it like extending it by Booleans, the part for like application and lambda calculus still would would stay exactly the same. One term which was like coined around this was one of true modularity. Like how can you basically like add new cases to a data type without like compiling existing code. And what is done in practice is that often, like if this is done, we have a lot of copy and paste. So basically like the repository which we have is copy and pasted. If you like want to test something out, we like go into a different branch. This branch might basically like go out of sync because we changed something in there, but then we don't basically like get it back to that. So this is basically a big hassle. And the question is whether we can avoid this kind of copy and paste. So if we look at, for example, Haskell, there are approaches out there, like for example, the data types a la carte approach by Sweerstra. And in this example, like features are defined as functors. So for example, like an inductive data type, like for lambda expressions would be like modularized, like basically like parameterized by this X of type, which I then use in the case of application and in the case of abstraction. And then later on, I can define a general expression type as a fixed point of this functor, saying, for example, like closing of this functor. And then you can define a variance which instantiate this general type with co-product of feature functors as I would have here. And I can assemble all the sphere type classes. So I would like to do something similar in the rock proof assistant, but the problem is that this general expression type is of course impossible in a proof assistant to write because it doesn't satisfy the positivity restriction. Okay. So there have been some solution out there, most of them all in this year from 2013. And the basic idea was to encode the kind of functor which we have, right? So encode the functor so that it actually like goes around this like positivity restriction, and we don't have to do this. So there are several very clever ways to do this, but the problem is that I can't like use internal mechanizations, like internal parts of a proof assistant, which makes it nice to use, right? So we would want to use a general like induction, constructor, et cetera, tactic of our proof assistant. And encoding this basically means that I would have to have to use this kind of directness. Okay. So one approach is that, which I want to briefly talk about now, is in this paper, Coq à la carte, which proposes a solution. And the solution which is proposed is that instead of having this like general inductive type, which induction type here, you basically do a compromise between having full modularity and having no modularity at all. We basically like replace this really general algebra type by something which says like, in the end, I just like need to know like how to compose something at a specific point, and at this specific point, the termination is actually there. So if at this point I basically like replace a functor, I won't have any problems with the positivity conduction. There's tool support to support this. So like we have some boilerplate generation and some assembling via meterrock. And we could actually like have some practical modular developments improvement from like previously like 1,000 lines of coders on like one of the case studies to around like 125 lines of code. Okay. Interest of time, I will skip on the demo, but like the important part is that we can basically like define data types and like features just as we would do otherwise in the proof assistant. So we can, for example, define this extension of X plus. We can define like a well-tightness relation. We can define an evaluation relation as we would have as an inductive proposition. And most of the assembling which we would have in a proof can be done either by using meta programming or by code generation, which has been done in the beginning. So you might ask how much this scales. This scales until basically like proving a proof like of strong normalization. So we can prove strong normalization in a modular way for a lambda calculus with Boolean sums, etc. And lines of code wise, this is not too different of what we would have if we would do it in a non-modular way. Okay. So this is the good news. The bad news is that library-wise, we had some problems with this. One is that we have a dependency on a very specific version of meterrock, so it doesn't work with the current version of rock which we're having now. So, which is of course like very bad library design in this case. It's very much of a proof of concept and could like use some like more mature use of tactics. We have an example of strong normalization, but really we would need to do it on like a bigger library, which was like done externally and look like basically like how it works to modularize this existing library. And the last part is that there's still like some parts that resemble a modular proof and need some overhead. So the real question is like, how willing would the developer of a library be? Like, what is basically like the difference which there would be allowed to be in such a modular library, so that we could, so that that people would be willing to put up with a modular. Okay. There are some more recent related work on a lean library or using lean's meta-programming facilities, and also some work based on family polymorphism. One thing I would be interested from people like writing libraries here is like I said before, like how different is basically a proof allowed to be used that you would be willing to basically like exchange modularity for an overhead. Okay. So this brings me to the end of the talk. So I showed you basically like to example one thing based on a very specific sample, like a library for binders, and then towards an approach to basically have a library for modular proofs. And thanks for your attention. Are there any questions?
Any questions?
So you mentioned that you can add new cases in your inductive types,
Yes.
but sometimes you also want to add parameters to your inductive types.
Yes.
So can you deal with that?
The library doesn't so far deal with it. I don't think there's a fundamental problem with doing so, but yes, doesn't do it so far.
A similar question. What about instead taking something with some constructs and so on and splitting data type into two, so the inverse is someone?
So far it doesn't do the splitting. So far it just does the assembling. But I think in the end, it should be able to do something like if you would have like a full library, which is not just like a proof of concept, it should actually be able to do some of these kind of transformations, also being able to split these kind of data types. And really, there isn't a fundamental problem in doing so. It's just like there. Thanks.
Okay, thanks.